Okay, we're rolling. Hello everyone, my name is Michael Peterson and welcome to my Exam 2 presentation. In this presentation we will cover the problem, some of the assumptions, drawing input and output, free body diagram 1, B equivalent, J, free body diagram 2, K equivalent, motion equations, and numerically 2D Laplace transformation, inverse Laplace transformation with MATLAB code, the code results, space representation, and then the matrices. Now this is the kind of the way how I did it, how I solved it out for this problem. I might miss a few things, might not be as fully organized, but I just kind of went through and made up this PowerPoint presentation as I worked it. So starting off with the problem, there's a lot of stuff to find. We had to do a drawing, we had to find some matrices, we had to find the motion equation, but you can see the problem that we're given on the right hand side here. And we have our direction, we have a torque, which will be important when I get into my drawing here in a bit. So let's just go over the assumptions first off. So in the assumptions, we're assuming the system is initially at equilibrium. The gear rotates in in clockwise direction. The gear is a round cylinder. The spring and damper are massless, and the spring will remain linear. With those assumptions, we can now look at the drawing and see my input and output decisions. So in the drawing, you have your two dampers, you have the gear. In the back here, there is a bar with its own like gear teeth, and then you have a mass, and then you have two springs, and then you have another damper here. Now, the reasoning I chose the input be x of s is because of the direction we were initially given, x going up. So when the mass is moving, the gear itself will rotate, which then gives us a torque, which then gives us our output of T of s. With that being said, now let's go into the free body diagram 1, which is pretty much like the first part of the top part of our diagram drawing. We got the gear, two dampers, and here's like the quick free body diagram drawing that I have on my work. We have our force going downward from here, and you got the torque, etc. And now we have our B equivalent and our J. So J is more for future reference, but I found it during when I was finding the B equivalent. So B equivalent equals B2 plus B3. We have our B2 and B3 being 2.1. That equals 4.2. And then we have our free body diagram for the second part of our problem. So here is the mass, and then we have the bar with the gear teeth on it, the two springs, and then the damper. So in the free body diagram, we have our Fy, our force going up, our damper force, and then the K equivalent, along with our M1 X double dot down, and then our X direction. So we now go into the K equivalent. We need to find that. So these are some statements that I've also made in. Don't know if they're necessarily relevant in any case in the future, but I'm putting them out here when I was looking at the problem. So our K equivalent equals K1 times K2 all over K1 plus K2. And we're given that K1 is 160, K2 is 20. Let's put them in the equation. We get K equivalent is 17.778 newtons per meter. The motion equation. So this was found with referring back to our diagram. Fy equals m1 x double dot plus b1 x dot plus b equivalent x. And then we have our torsion motion equation, which is T equals jx double dot all over r radius plus fyr plus b equivalent x dot all over r. So algebraically, we pretty much combine them together, and this is what we get. And now numerically, you put in the values, where Fy equals all this, which is our equation 1, and then our T equals all this, which is our equation 2. You then combine the equations 1 and 2 to get equation 3. T equals 25.25 x double dot plus 18.5 325 x dot plus 1.05x as our equation 3. Now you take that equation and put it, and you do the 2D Laplace transformation. So you have your TS equals all this mess, and then you take out your XS, which then you're left with this, and then you move everything around to eventually get this equation. This is kind of important when we get to MATLAB coding. So when we get to the inverse Laplace transformation with MATLAB, you took these values right here and input them as your den in your code. And then you have your step system, grid, and then this is where the real inverse Laplace happens. So you have your num1 den, which is all this stuff right here, inputted into this, and you needed the 0 out here so that you can move it to the proper derivative. Because if you did it this way, it wouldn't be high enough when it solved out the results. So then you have all your functions and stuff, and now you have the code result. You end up with the ft time domain being this whole thing right here. You have your step response graph, amplitude, time, second graph here. You then will have our space representation formula to solve out. And taking equation 3, before we did the Laplace to it, we now then have to set everything equal to x double dot. So then you move this, move everything over to the t section. You divide everything by 25.25. You then have your space representation equation. Now we have matrices. So we have our state variables, x1 equals x, x dot 1 equals x dot, x2 equals x dot, x dot 2, x2 dot equals x double dot. You now have your matrices from this equation with these state variables into making this thing. You have your B equivalent over your radius, the B1 over mass 1, etc. So now you have your output equation, which we have y1 equals x equals x1, y2 equals x dot equals x2. Then you have your x dot equals ax plus by, then your y equals cx plus dy. And then you have the matrices from this equation here, y dot 1, y dot 2 equals all this. And then you have this same equation here with your values plugged into it, leaving you with this matrix. There's a lot to cover in a very short time frame of 10 minutes, but hopefully I kind of got enough in there, and then you can still look through a lot of my hard work. And so if there's any questions, comments, and or concerns, or anything that I missed, please do not hesitate to ask or let me know. Thank you for your time. Have a good day.